Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on December 31st, 2025, just about 3 days ago. It introduces Dream2Flow, a novel framework that bridges the gap between generative video models and robotic control by using 3D object flow, enabling robots to manipulate diverse objects without task-specific training. The paper is titled Dream2Flow, Bridging Video Generation and Open-World Manipulation with 3D Object Flow. And as we'll see shortly, the method's ability to handle everything from granular materials to articulated objects is quite remarkable. Figure 1 illustrates the core pipeline. On the top left, the process starts with a text instruction and an initial image, which a video model uses to generate a clip of the task being performed, typically by a human hand. Next, the middle panel shows how the system extracts 3D object flow from this video, converting the visual motion into precise 3D trajectories, seen here as rainbow-colored lines. On the far right, the robot executes these trajectories to open the oven. Finally, the bottom rows highlight the versatility of this approach, demonstrating successful manipulation of rigid furniture, deformable cloth, and even granular pasta. Figure 2 details the exact pipeline. It begins on the far left with the text instruction. Put the bread in the bowl, paired with an initial RGBD observation. These inputs feed into a video generation model, which synthesizes a video of the task, seen here as frames of a human hand moving the object. In the center blocks, the system extracts video depth and 2D tracks from that synthetic video to compute the 3D object flow. Finally, on the right, the robot policy translates those 3D flow trajectories into actual motor commands to complete the task. So Figure 6 shows how this 3D object flow serves as a universal reward signal across different robot bodies. In the top row, a standard Frankapanda arm successfully pulls a door open. The middle row features a spot robot, which learns to shift its mobile base for better leverage. Finally, the bottom row displays a humanoid, the GR1, which adopts a stable pulling grip. Because the system tracks the object rather than the robot, it allows each distinct machine to discover its own optimal strategy. Table 3 now shifts focus to the video backbone itself, comparing WAN 2.1, Kling 2.1, and Veo 3. In the simulation column for Push-T, WAN 2.1 is the clear winner with 52 successes out of 100. But for the real-world OpenOven task, Veo 3 takes the lead, succeeding in 8 out of 10 trials. This performance gap happens because Veo 3 creates more physically consistent videos, avoiding the morphing artifacts that plagued the other models in complex real-world scenes. Alright, Table 1 compares Dream2Flow against two alternative methods, A versus DC and RigVid, across 3 real-world tasks. In the first row, Bread and Bowl, Dream2Flow achieves 8 successes out of 10, edging out the baselines. The difference becomes much starker in the OpenOven task, where A versus DC fails completely with 0 successes, while Dream2Flow matches its previous high of 8. Finally, for the difficult cover bowl task, which involves deformable cloth, performance drops across the board, yet Dream2Flow still maintains the lead. Table 2 validates the quality of the training signal by comparing it to a perfect ground truth. The top row shows success rates using the object state reward, which relies on privileged simulator information, while the bottom row uses the method's visual 3D object flow. Across the Franka, Spot, and GR1 robots, the results are nearly identical, with success rates consistently hitting 99 or 100%. This confirms that the extracted flow is accurate enough to serve as a robust reward for reinforcement learning, effectively matching the performance of direct state access. Wrapping up, the key insight here is that 3D object flow effectively bridges the embodiment gap by focusing on the object's motion rather than the agent's body. This allows off-the-shelf video models to serve as zero-shot physics simulators for diverse materials, from rigid doors to granular pasta. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.